Welcome to the deep dive. We are cutting through the noise today to really examine a fundamental tension, I think, in modern AI. How do we actually get trust and, verifiable quality, but do it at scale? We're talking specifically about knowledge graph construction today and how you can do it efficiently, especially in these high-stakes environments.
Yeah, that efficiency piece is key.
So we're diving deep into this paper, GraphMERT, Efficient and Scalable Distillation of Reliable Knowledge Graphs from Unstructured Data. Now, for decades, the AI community has been chasing this big promise of neurosymbolic systems, right?
Right, the best of both worlds.
Exactly, combining neural network generalization, that pattern matching power, with the kind of symbolic abstraction and reasoning. But, well, that ideal framework, it's consistently failed on two really practical metrics. Scalability, sure, but maybe more importantly, reliability.
Definitely reliability.
And this failure, it's particularly pronounced when you move into these specialized high-stakes domains, like medicine, finance, maybe even law.
Indeed. And the authors of this GraphMERT paper, they really understand that the mission isn't just, grabbing data. It's about automatically deriving a reliable knowledge graph, a KG, from huge amounts of text.
Okay.
And to get there, they set up two, let's say, non-negotiable criteria for what reliability actually means in this context. First is factuality.
Right.
This absolutely demands clear provenance. So every single fact you pull out, it has to be instantly traceable, verifiable, back to the specific bit of source text it came from. No ambiguity.
Super important.
And second, validity. This means the relationships you extract, they have to strictly follow a predefined ontological schema, the rules of the domain.
Right.
Because in a clinical setting, for example, a fact might be technically true in isolation, but if it violates the domain's structural rules, well, it's useless, or actually, it could even be dangerous.
Yeah, I can see that. And this is the surprising hook that really grabbed our attention right away. GraphMERT, the framework they built, it uses an incredibly compact model. We're talking just 80 million parameters.
Tiny by today's standards.
Right. Now, contrast that with the baseline they used in the paper, a 32 billion parameter LLM Qwen 3.
Orders of magnitude different.
Exactly. And not only is the little GraphMERT model way more efficient than compute deployment costs, but the KG it produces is significantly better in quality. Specifically when they tested it on crucial medical texts from PubMed about diabetes. This isn't just, a little bump in performance. This feels like a radical challenge to the idea that just scaling up is the only way to get advanced capabilities.
It really questions that whole bigger is always better mantra, especially for specialized tasks.
Okay, so let's maybe situate this work first. Thinking historically about AI paradigms.
Right.
We've seen this constant back and forth.
Yeah, the pendulum swing.
You had the symbolic systems, GeoAI, things like expert systems, great for interpretability, sound reasoning, But they were brittle. They struggled to scale because of that combinatorial explosion of rules.
Right, the knowledge engineering bottleneck.
Then came the neural revolution. Deep learning, suddenly you've got immense scalability, amazing generalization, pattern recognition, but, well, the cost was opacity, those black boxes. And their reasoning is often probabilistic, sometimes brittle. So neurosymbolic AI, the dream is to harness that deep learning power, but impose the rigor, the accountability of symbolic representation.
And this is precisely where even today's massive large language models, despite all their general smarts, they really falter when you ask them to build high-fidelity KGs. The gaps aren't small. They're kind of fundamental to how these models work.
Okay, so what are the main gaps?
Well, first, there's the whole issue of opacity and probabilistic reasoning. LLMs are black boxes, right?
Yeah.
We don't really know the exact path they took to generate a specific triple.
Right.
Their reasoning is statistical, it's probabilistic. That makes them inherently bad at guaranteeing things like causal inference. And this leads straight to that notorious problem, hallucinations.
Ah, yes.
Yeah.
Making stuff up.
Exactly. Generating content that's just not grounded in the source text or flat out contradicts it. And this gets even worse during multi-step reasoning, which is absolutely essential if you want to compile real knowledge.
Okay, opacity. What else?
Then there's domain expertise, or lack thereof sometimes. A 32 billion parameter model, yeah, it's trained on the whole internet, basically. But that breadth often means sacrificing depth. It just doesn't have the critical, nuanced understanding, the specific semantic definitions you need for specialized fields. Think pharmaceutical research or maybe complex financial regulations. When you're dealing with very specific ontologies, the LLM's general knowledge base just isn't precise enough.
It speaks English, but not necessarily medicine or law.
Pretty much. Then there's provenance. Accountability.
Yeah.
Standard LLM extraction methods, especially just prompting it like extract triples, they completely fail this test. Well, the knowledge the LLM generates, it's implicitly smeared across billions of weights inside the model. You can't easily point to a specific sentence in a source document and say, that's where this subject-predicate-object triple came from.
Right. No audit trail.
Exactly. And without that verifiable source attribution, any claim of reliability in a high-stakes setting just evaporates.
You'll say that's the big one. And you mentioned one more.
Yes, the locality bias. LLM extraction often happens just within the immediate context window of the prompt you give it.
Right. What it can see at that moment.
Precisely. And this encourages the model to link things just because the terms happen to appear close together in that chunk of text.
So correlation, not causation. Or even just co-occurrence.
Exactly. It leads to extracting spurious correlations, false facts cooked up just from local proximity, rather than capturing global, universal facts that hold true across the entire corpus. And just making the context window bigger doesn't really fix it. Often it just introduces new problems, like the model getting distracted or hallucinating even more because it can't manage attention over such a huge input.
So it sounds like standard LLMs are just not built for this kind of rigorous, reliable KG construction out of the box.
That's the core argument. And to counter these flaws, the GraphMERT paper lays out 6 really specific requirements. Think of them as the design goals for any system that wants to do this properly, especially in an enterprise setting.
Okay, what are they?
The first 3 focus on quality and the process itself. 1, factuality and provenance, like we said, grounding, citation mandatory.
Got it.
2, validity. All the extracted triples have to obey the rules, the ontology constraints, no exceptions.
Makes sense.
3, automation. The system needs to be end-to-end. We needed to get away from needing armies of experts, handcrafting rules, or doing manual feature engineering like in the old days.
Right, scalable automation. What about the other 3?
Those focus more on utility and scale and deployment. 4, scalability. Performance has to stay solid even as your data grows, your corpus gets bigger. And GraphMERT addresses this with its tiny 80 million parameter size.
Compared to billions, yeah.
5, domain generality. The underlying ideas, the architecture, it should be principle-based. You should be able to transfer it to other specialized areas without a massive re-engineering effort each time.
Okay.
And 6, global integration. The system has to build knowledge across all the documents, linking concepts from the whole corpus, not just getting trapped in those local co-occurrences within a single document.
Right. Escaping that locality trap.
Yeah.
Okay. 6 clear requirements. And how did the big LLM baseline, the Win332B, actually stack up against these when they tested it?
Well, the quantitative results, especially on that PubMed diabetes data, they really highlight the failure of just throwing scale at the problem. They use these specialized metrics designed specifically for KG quality.
Like what?
Okay, so FACT score. This measures the percentage of triples that are both factually correct and logically aligned with the source text. The LLM KG. It scored a pretty dismal 40.2%.
Oof. Less than half.
Yeah. Whereas the GraphMERT KG reached 69.8%.
Wow, that's a massive difference. Almost 30 points.
It's staggering, right? Especially when you remember the huge difference in model size and compute resources. And maybe even more telling was the validity score. This strictly measures adherence to the ontological schema, the rules.
Okay.
The huge LLM's KG was only 43.0% valid. GraphMERT, 68.8%.
The big model is basically making up its own rules half the time.
That's a good way to put it. It confirms the LLM really struggles with what the paper calls predicate hygiene. It constantly confuses or even reverses the relationships defined in the domain ontology. It fails to respect the structural rules governing medical concepts. It might, know a lot of words, but it doesn't actually know the rules of this specific specialized game.
That paints a pretty clear picture. That level of failure really demands a different approach, not just more parameters.
Exactly. It necessitated a structural, domain-tailored solution like GraphMERT.
Okay, so that massive failure, the big LLM, really sets the stage. Let's pivot now and really look under the hood at what the researchers actually built. We're moving away from these giant, opaque, decoder-only models towards GraphMERT, graphical multidirectional encoder representations from transformers. An 80 million parameter encoder-only transformer specifically engineered for this kind of high-precision knowledge distillation.
Right. And the real cleverness of GraphMERT, I think, starts with tackling a fundamental problem. How do you get a model that's inherently sequential, like a transformer, to properly understand graph structure? Their answer is this novel input format they call the leafy chain graph.
Leafy chain graph. Okay, tell me about that.
Okay, imagine your original source sentence, the text, as sort of the main trunk or the roots of a tree-like structure.
Hmm.
The leafy chain graph formalizes this. It unifies the semantic, triples the knowledge you want to inject in the syntactic text into one joint sequential structure that a transformer can actually process.
Okay, so text and facts together in the input sequence.
Exactly. The roots of this chain graph hold the syntactic information, the actual tokens from the source sentence, and then attached to these roots are sparse leaves. These leaves hold the semantic knowledge, the subject, predicate, object triples that are relevant, derived from some seed KG.
Interesting. How sparse are the leaves?
The architecture enforces a fixed regularity, which is actually pretty important. They use 128 root nodes, and each root is connected to exactly 7 leaves. This results in a fixed input sequence length of 10,024 tokens every time.
Ah, okay. That fixed size probably simplifies things a lot for the model.
It does. It simplifies the whole encoding process before the tokens even get to the main transformer blocks. You're essentially embedding structural information right into the sequence format itself.
So you're kind of priming the transformer to expect relational data right from the get-go.
Okay.
That makes sense for the input format. But how does GraphMERT actually process the symbolic knowledge in those leaves? You said it's not just a standard encoder like Roberta. It's got this hierarchical graph attention network, HGAT.
Exactly, HGAT. This mechanism is integrated right into the embedding layer. Think of it as the relational encoding engine working before the main transformer layers.
Okay, how does it work?
So when you inject a semantic triple, say, head, relation, tail, into the leaves attached to the relevant head-tail tokens in the root sequence, HGAT gets to work on the tail part. It takes every single token embedding of the tail expression, and it fuses it with two things: the embedding for the specific relation involved, and the embeddings of all the head tokens it's linked to.
Whoa, okay, so it's packing a lot of context in there.
It really is. Functionally, this process encodes the full semantic triple context, the subject, the verb, the object, directly into the embedding space of the tail tokens. It's essentially telling the model, this token isn't just, say, density in isolation, it's density in the specific context of bone mineral density, and the relation has finding site.
I see. So even before regular self-attention kicks in, the token embeddings themselves are already aware of the relations and the entities they're connected to in the graph structure.
Precisely. They are relationally and structurally aware right from the embedding layer.
Okay, so the HGAT injects the relational meaning. And I think you mentioned earlier, if you mask out a leaf node during training, that helps train the relation embeddings themselves.
Exactly right. By masking out those leaf nodes, the tail expressions, you force the model to predict the full semantic concept. This naturally enables backpropagation through the HGAT mechanism. And that allows the model to learn the abstract underlying meaning of relations. Like, what does treats really mean semantically versus contraindicates? And it learns this independent of the specific words, the surface syntax, used in the original source sentence.
So that's how this relatively small ADM model can learn high-quality relational concepts that the big general-purpose LLM often misses, because the LLM might just be looking at word co-occurrence.
That's the idea. It's abstracting relational knowledge away from just brittle lexical patterns.
Okay, that makes sense for relational encoding. But what about the graph structure itself? Transformers are good at sequential distance, right? Position embeddings and all that. How did they get the attention mechanism to respect the graph distance in this leafy chain graph structure?
Good question. They introduced something called an attention decay mask. It's a modification to the standard self-attention mechanism.
Okay.
First, for any two nodes warn you dollars in this combined leafy chain graph structure, they calculate the shortest path distance between them using the standard Floyd-Warshall algorithm. That gives you a matrix of all pairs' shortest path distances.
Right, standard graph algorithm.
Then they take the standard attention weights, the ones calculated by the transformer based on query key similarity, and they modify them based on this graph distance.
Do they just zero out attention to distant nodes?
Not quite zeroing out, but decaying it. The core idea is that the attention affinity, how much one node attends to another, should decrease as the structural distance between them and the graph increases. They implemented an exponential decay function.
Exponential decay based on path distance.
Exactly. This decay factor is multiplied element-wise with the standard attention weights. So a node pays much less attention to nodes that are far away in the graph structure, even if they happen to be relatively close sequentially in the flattened 1024 token input. It prioritizes neighbors defined by the actual graph connections.
Interesting. Any specifics about the decay function?
Yeah, they found that a simple linear decay wasn't optimal. The function they use involves the square root of the path distance within a GEU activation, all raised to the power of a hyperparameter lambda, and includes a learnable parameter p. It sounds complex, but the key intuition is it provides a smoother, more controlled decay curve that better models the relationships in these specific sequence graphs they constructed.
So the attention mechanism itself becomes structurally aware throughout the model's layers.
That's the goal. It forces the transformer layers to respect the graph topology, not just the linear sequence order.
Okay, let's switch gears slightly to the pre-training objective. The model isn't just learning one thing, it's training on two tasks simultaneously, right?
Correct. It's a joint objective. You have the standard masked language modeling, MLM, working on the syntactic tokens in the roots, predicting masked out words in the original sentence.
Like Bert or Roberta.
Exactly. And then you have the novel masked node modeling, MNM, which works on the semantic leaves, predicting the masked out tail expressions of the injected triples. The final loss is just a weighted sum of the MLM loss and the MNM loss, balanced by a hyperparameter they call dial fits.
And the masking strategy itself. You mentioned there's a nuance there, especially for the semantic leaves.
Yes, this is quite important. For the syntactic tokens in the roots, they use a span-BERT style masking. So they mask out contiguous spans of words, encouraging the model to predict multi-word phrases.
Okay, standard practice for MLM these days.
But for the semantic leaves, the strategy is different. When leaf span is chosen to be masked, which happens with a certain probability, they mask the entire leaf span, not just a few tokens within it, but the whole thing.
Okay. Why the full span mask specifically for the leaves? What's the advantage over just masking a part of the tail expression?
The rationale connects directly back to training those high-quality relation embeddings via each J. Think about the full semantic meaning of a relational tail, like a disorder characterized by hyperglycemia. That meaning really emerges from the complete multi-token phrase.
Right, it's a unit.
Exactly. If you only masked out, say, hyperglycemia, the gradients flowing back to the relation embedding might only capture a fragment of the full semantic meaning. By masking the whole leaf, they ensure the model has to predict the entire conceptual unit, forcing the gradients to capture that full, complex semantic meaning.
I see. So it forces the relation embeddings to become more robust, to represent the meaning of the entire tail concept, not just bits and pieces based on co-occurrence.
Precisely. It's vital for helping the compact ADM model learn those abstract relational representations that allow it to compete with and even outperform the massive 32B baseline. Okay, so before GraphMERT even gets trained, there's a crucial step, really a philosophy: data quality first. The system deliberately avoids training on just massive, noisy web dumps.
Right, no general web corpora.
Instead, it focuses exclusively on a limited set of expert-verified open-source texts. In this specific case, for the diabetes domain, they used PubMed abstracts, high-quality, domain-specific data.
That focus on clean data seems absolutely fundamental if reliability is the main goal.
Yeah.
Okay, so to train the model, they obviously need that seed KG you mentioned to provide the initial set of valid relations and semantic examples. Where did that come from for the diabetes work?
They leveraged the Unified Medical Language System, UMLS, specifically focusing on the SNOMED, CT, and gene ontology vocabularies within UMLS, which are standard resources in biomedicine.
Okay, standard medical ontologies, but getting the relevant facts from UMLS and into those leafy chain graphs sounds like a challenge in itself. How did they prepare the seed KG?
It's a really careful multi-stage process designed to inject only the most relevant and diverse knowledge, avoiding noise. There are 3 main stages.
All right, stage 1.
Stage 1 is entity linking. You need to map the entities mentioned in the raw text, like diabetes mellitus, to their standardized concepts in UMLS, which are called concept unique identifiers, or CUIs.
And getting that mapping right is critical. How'd they do it?
They used a pretty robust 2-step filtering process. First, for candidate retrieval, they didn't just use general embeddings. They used SABR.
Suburbs, okay. What's special about that?
It's another encoder-only model, but it's specifically pre-trained on a massive amount of biomedical text and terminology from PubMed.
Cool.
So it has a much better innate understanding of conceptual similarity within the biomedical domain compared to general models. It retrieves the top candidate CUIs from UMLS based on embedding cosine similarity.
Okay, so SABR finds conceptually similar candidates. What's the second step?
The second step is a sanity check using simple Jacquard string similarity. Just because two concepts are related doesn't mean the name matches well. So a candidate CUI retrieved by Sabert is only confirmed as a valid link if its Jacquard score, comparing its name to the original text entity, is above a threshold of 0.5.
Ah, so it needs to be both conceptually close and look textually similar. A nice safety check.
Exactly. It minimizes those incorrect links.
Okay, so entities are linked reliably. What's stage 2?
Stage 2 is contextual triple selection. Now, a single CUI in UMLS, like diabetes mellitus, might be linked to thousands of facts or triples in the full ontology,
Right.
but only a small fraction of those are actually relevant to the specific sentence or abstract you're processing right now. Injecting irrelevant facts would just be noise for the model.
So how do you filter for relevance?
They use embeddings again, this time from the Gemini model. They calculate the cosine similarity between an embedding of the potential UMLS triple, linearized into text, and an embedding of the original input text sequence.
Okay, comparing the fact to the context?
Precisely. This lets them rank all the available triples associated with the linked entities in that sequence and keep only the top 40 most contextually relevant ones. It's a crucial pruning step to keep those semantic leaves highly relevant to the local text.
Top 40 per sequence. Okay, that seems reasonable. Now, stage 3, you mentioned an injection algorithm. Why wasn't just taking those top 40 contextually relevant triples good enough? What bias did they need to fix?
This is a subtle but really important point. If you just naively take the top 40 triples based purely on that contextual similarity score, you introduce a significant relational bias.
How so?
Well, very common, often less informative relations, think classification links like ISA or very general structural relations, tend to show up and score highly across many different documents just because they're so frequent.
Ah, okay. So you'd end up training the model mostly on isolinks.
Exactly. Your training data for relations becomes heavily skewed. The model learns really well how to predict ISA, but the embeddings for rarer, perhaps more scientifically interesting relations remain weak or underdeveloped because they hardly ever made it into the top 40.
Right, the model's relational vocabulary becomes impoverished. How does the algorithm fix that?
It solves this by jointly optimizing for two things. The contextual score, using a pretty strict threshold, alpha Palantong 5555, so only highly relevant triples are even considered, and relation diversity.
Okay, how does it balance those?
It works iteratively. As it selects triples to inject, it doesn't just pick the next highest scoring one. It actively prioritizes triples belonging to relation types that are currently underrepresented in the set of triples already selected for that sequence.
Ah, like affirmative action for rare relations.
Kind of. It ensures that these rarer but potentially very valuable relation types don't get squeezed out by the common ones. This forces the final seed KG injected for each sequence to be a much more robust and diverse sample of the domain's overall relational structure.
That's clever.
Yeah.
Okay, so the data's clean, the seed KG is prepared and injected with diversity in mind, the model's trained. Now, the final triple extraction pipeline, how does it actually generate new knowledge? You said GraphMERT is encoder-only. It predicts tokens, not full sentences.
Right. So during the extraction phase, GraphMERT operates purely using that M&M objective we discussed. You feed it a text sequence, you specify a head entity that's already linked in the text, and a relation type you're interested in. You mask out the corresponding semantic leaf nodes in the input, and then you run the model forward. Its output is essentially a probability distribution over the entire vocabulary for each masked token position in the leaf. From this, you take the top K most likely tokens they use, K20 in the paper, for each position.
Okay, so you get a list of, say, 20 candidate words for each position in the missing tail expression. But that's just a jumble of tokens, right? How do you get a coherent, grammatically correct, multi-word tail like a disorder characterized by hyperglycemia?
That's where the helper LLM comes in. In this case, they use the same Quinn 332B that failed as the primary extractor.
Wait a second. If you still need the giant 32 billion parameter LLM at the end, doesn't that kind of undermine the whole efficiency argument of using the tiny ADM GraphMERT model? Are we just shuffling the cost around?
That's a really fair and crucial question. The key defense here is that the helper LLM's role is fundamentally constrained and much narrower than full KG extraction.
How constrained?
The small, efficient GraphMERT model does the heavy lifting. It performs the actual knowledge distillation. It identifies the core semantic content, the specific tokens that represent the factual answer, grounded in the text and respecting the relation type. The helper LLM's job is much more limited. It's essentially linguistic polishing.
Polish.
Yeah. It takes the original sequence context, the given head relation pair, and crucially, only those top 20 candidate tokens predicted by GraphMERT for each position. Its task is simply to arrange a subset of those specific tokens into a coherent, grammatically sensible multi-token tail expression.
Ah, so the helper LLM cannot invent any new information. It can't use any words that weren't suggested by GraphMERT.
Exactly. It's strictly forbidden from introducing new entities, new relations, or any tokens outside that pool provided by GraphMERT. Its role is highly restricted. It's a sophisticated sequence assembler or grammar checker operating within a very tight, fact-constrained sandbox defined by the small, reliable model.
Okay, that makes a big difference. So GraphMERT handles the what, the factual content, and the helper LLM handles the how, the linguistic form, but only using GraphMERT's ingredients.
That's a perfect way to summarize it. And even after the helper LLM constructs a potential triple, there's one final safety check.
Another one.
Yep. The extracted triple undergoes a final similarity check against the original source sequence embedding using another strict cosine similarity threshold, beta $0.6777.
Lightest final check.
It filters out triples that might be grammatically fine and use the right tokens, but are perhaps too generalized or have drifted too far from the specific meaning of the source sequence. If the generated triple doesn't strongly resemble the informational content of the specific sentence it supposedly came from, it gets rejected.
So it's inherently suspicious of its own output, demanding high relevance right to the end.
Exactly. It ensures the final KG remains highly sequence-specific and factual. And critically, this whole process ensures that every single triple that does make it into the final KG is traceable back to its original source sequence and the specific head relation query that generated it. That's how they guarantee the verifiable provenance that was requirement number 1.
Okay, let's really dig into the results now. We already touched on the headline figures for the triple-level evaluation. That huge gap in fact score, nearly 70% for GraphMERT versus about 40% for the LLM baseline, is striking. But the paper went deeper, right? They analyzed why the big 32B Qwen3 model failed so badly in this specific task. What were the common failure modes they saw?
Yeah, they did a careful qualitative analysis using Qwen3 itself as a judge, actually, which is interesting. They consistently found 3 major types of systematic failures when using the general-purpose LLM for this kind of structured extraction.
Okay, what's the first one?
First was relation misinterpretation. The LLM often seemed to map relations based on sort of surface-level word associations rather than the strict ontological definitions.
Can you give an example?
Sure. The paper mentions it generated the triple-angle diabetes, Hass-finding site, urban area wrangle. Now, in the medical ontology, Hass-finding site is meant for anatomical locations, like where a symptom manifests.
Right, like pain has finding site abdomen.
Exactly. But the LLM confused this specific clinical definition with a generic idea of location, probably because diabetes in urban area might co-occur statistically in discussions about demographics or epidemiology in its training data. It's making a common sense association that completely violates the domain's specific rules.
A classic domain knowledge failure. Okay, what was the second failure mode?
Overlinking. This suggests maybe a lack of confidence or perhaps just trying too hard to find connections.
What does that look like?
They found cases where the LLM would assign multiple, sometimes up to 7, different relation types to the same pair of entities. For example, between obesity and diabetes, it might assert associated with, causes, precedes, coexists with, exacerbates, etc., when maybe only 1 or 2 of those are actually valid or the most appropriate according to the specific ontology and context.
So it's just throwing relational spaghetti at the wall and hoping something sticks.
That's a pretty good analogy, yeah. It lacks precision and specificity.
All right. And the third failure mode?
This one ties directly back to that locality problem we talked about earlier. Spurious co-occurrence links.
Linking things just because they appeared near each other.
Precisely. The example given is generating Langle diabetes, Has method, mammography, wrangle, why? Simply because those 2 terms happen to appear close together in some specific text abstract, maybe discussing screening guidelines for diabetic patients.
Right. There's no actual semantic has-method relationship there in the general case.
None at all. The model inferred a formal link based purely on statistical proximity in its limited context window. It's basically guilt by association at the textual level. And this really highlights why you need a method like GraphMERT that enforces structure and tries to capture more global, reliable facts.
Those 3 failure modes paint a very clear picture of why the general LLM struggled. And GraphMERT's high validity score, 68.8% versus 43%, directly confirms it did a much better job sticking to the ontological rules that predicate hygiene. They also did a sanity check using GPT-4. The paper refers to it as GPT-5 thinking, likely an internal term or future placeholder, as a kind of expert qualitative judge, right? Focusing on some high-value, complex concepts like IGF-1. What did that reveal?
Yeah, that qualitative check was very insightful. It basically confirmed that the GraphMERT KG is much more conservative and domain appropriate in the knowledge it generates. For IGF-1, for example, the GPT judge marked 68% of the triples generated by GraphMERT as valid and correct. Yes, triples.
Okay. And the LLM KG?
Only 28%. A huge difference again. But just as important was the type of errors each system made.
How did the errors differ?
GraphMERT's errors tended to be things like slightly vague or incomplete tails. Maybe it missed a specific adjective or modifier token. These were mostly errors of omission or slight underspecification, likely stemming from the constraints of using that fixed pool of predicted tokens and the helper LM's limited combination ability.
So less harmful errors, perhaps.
Arguably, yes. The LLM errors, on the other hand, were often fundamentally more severe. They saw things like outright semantic relation reversals, mixing up cause and effect, or really deep ontology violations. The paper mentions examples like the LLM mixing socioeconomic concepts like lockdown with biomedical concepts like bone mineral density using completely inappropriate relational predicates.
Wow.
It really shows the LLM projecting its massive general-purpose statistical world knowledge onto a domain where highly specific, rigorous structure is paramount and failing to adapt.
Okay, so the triple-level evaluation is clearly in GraphMERT's favor. But what about the graph as a whole? Does a collection of more accurate triples actually lead to a more useful knowledge graph for downstream tasks? How did they test that?
They did a graph-level evaluation using a technique called GraphRag. They plugged both the GraphMERT-generated KG and the LLM baseline KG into a retrieval-augmented generation system designed for question answering. They used the ICD Bench Medical QA benchmark.
Okay, so testing the practical utility of the KG for reasoning.
Exactly. This kind of task often requires multi-hop reasoning over the graph to find the answer, and the results showed a clear utility gain for the GraphMERT KG.
What was the gain?
The system using the GraphMERT KG achieved an overall QA accuracy gain of 9.2 percentage points compared to using the LLM KG. It went from 50.2% accuracy with the LLM KG up to 59.4% with the GraphMERT KG.
That's quite significant for a complex QA task.
It is. It demonstrates that the higher factuality and structural validity at the triple level translate directly into improved performance for applications that rely on that knowledge structure for reasoning. Essentially, a cleaner, more precise KG acts as a better grounding mechanism for the RAG system, helping to mitigate the LLM's tendency to hallucinate when trying to follow reasoning chains.
That makes perfect sense. Okay, let's quickly touch on the ablation studies. These are always important, the experiments where they take parts of their system away to prove those parts were actually necessary.
Right, the engineering reality checks. The hyperparameter sensitivity study was particularly revealing, I thought.
Parameters.
Those similarity thresholds we talked about. Alpha for seed KG injection relevance, and a beta for final triple acceptance relevance. They found that performance, measured by FACT score, peaked exactly at the strict values they chose. Alpha 5555 and beta $6.67.
What happens if you relax those thresholds?
Performance goes down. If you lower alpha, you start injecting noisier, less relevant triples into the training data via the seed KG. If you lower beta, you start accepting generated triples that are less faithful to the source text. The fact that peak performance requires these strict thresholds really hammers home a central theme of the paper. Rigorous quality control at every stage is paramount.
So quality over quantity, especially in the training data. It suggests low-quality training data might actually be worse than having less data overall.
Precisely. The system is designed to be inherently selective, almost suspicious, of the information it uses and produces.
Okay, what other ablations did they run? Seed KG sparsity.
Yes, they tested how robust GraphMERT was if it started with a much weaker seed KG. They randomly removed up to 75% of the triples from the original UMLS seed KG before training.
And how did it cope?
Remarkably well. Even with only 25% of its initial seed knowledge remaining, GraphMERT still outperformed the full 32B LLM baseline KG, built with access to its vast implicit knowledge by almost 4 percentage points in fact score.
Wow, so it's not just memorizing the seed facts.
Not at all. It indicates the model is effectively learning deeper, transferable relational abstractions and structural patterns from the data and the architecture itself, likely thanks to mechanisms like HGAT. It can generalize reasonably well, even from a sparse starting point.
That speaks volumes about the learning process.
Yeah.
Okay, and the final key ablation, what happened when they took out HGAT, that core graph attention mechanism in the embedding layer?
That basically broke the system for semantic prediction. When they removed HGAT and just used a standard Roberta-style transformer embedding, the accuracy plummeted.
How did the output change?
The researchers observed that the top token predictions for the mask sleeves became dominated by completely irrelevant syntactic stuff, things like commas, articles, or common stop words, rather than meaningful semantic concepts.
So just noise, basically.
Pretty much. It proves that the HGAT layer is absolutely essential. It acts as that crucial structural filter, fusing the relational meaning into the leaf embeddings right at the start, compelling the model to focus on predicting high-value semantic tokens relevant to the relation instead of just common syntactic filler. The architectural choice was clearly non-negotiable for getting meaningful output.
That makes sense. They also mentioned an interesting trade-off with the masking strategy, didn't they? Replacing the span masking, MNM, with simpler single-token masking.
Yes, that was quite subtle. Using single-token masking actually resulted in a slightly higher validity score.
Higher validity. Why would the overall KG utility decrease then, as they reported?
Because the token-level masking encouraged the model to generate lots of very short, often trivially correct triples, things like Langle diabetes, Zelza, disease wrangle up. These are simple, usually valid according to the ontology, so they boost the validity score.
But they aren't very informative.
Exactly. They lack the complexity and granularity you need for deeper multi-hop reasoning tasks like the QA benchmark. The span masking MNM technique, while maybe producing slightly more complex tails that occasionally tripped the validity check, leading to a slightly lower score, was essential for generating those richer multi-token expressions that actually encode the detailed domain facts needed for real-world applications.
So it's a good reminder that optimizing for one metric, like validity in isolation, might not lead to the most useful overall result. You need to consider the end goal.
Absolutely. Utility in downstream tests is often the better measure of the KG's true quality. #OurTrust.
Well, this has been quite the deep dive. I think it's clear that GraphMERT really represents a significant step forward in trying to build an efficient, scalable, but also transparent neurosymbolic stack.
You've got this tiny 80 million parameter model doing the heavy lifting of neural abstraction learning, and then translating that learning into these high-fidelity symbolic knowledge graphs that you can actually use for verifiable reasoning. The central takeaway for me seems undeniable. Shifting focus towards meticulous, high-quality, domain-specific data and really tailored architecture can fundamentally trump just throwing brute force scale at the problem.
I agree. And the modular structure that GraphMERT enables, that's really key for achieving reliability and long-term value, especially in sensitive areas.
Yeah.
Because the knowledge ends up distilled into an explicit KG, something that's auditable, editable.
Right. Domain experts can actually look at it, verify it, even correct or update facts directly.
Exactly. Without needing to retrain a massive neural network from scratch, which is often impractical. That kind of transparency and accountability is just...
Oh, it's non-existent if your knowledge is purely stuck inside the implicit weights of a giant neural model. Trying to remove one bad piece of knowledge from an LLM can risk catastrophic forgetting or unpredictable side effects. So by focusing on knowledge depth and structure over just statistical breadth, this work really feels like a strong proof of concept for moving towards more specialized, domain-specific intelligence that we can actually trust and manage.
That auditability, the transparency, the verifiable provenance tracing back to the source, that directly addresses the critical needs of domains like medicine, finance, law, where errors have real significant consequences. It feels like it transforms the AI from just an opaque, probabilistic pattern matcher into something more like an accountable, verifiable knowledge distiller.
Well put.
So to leave you, our listeners, with a final thought to mull over, the paper does acknowledge that final reliance on the 32 billion parameter helper LLM for stitching together those GraphMERT predicted tokens into fluent multi-token tails. It's constrained, yes, but it's still there.
A necessary component for now.
If GraphMERT itself is purely encoder-only, designed for prediction. What specific architectural advances might we see next in encoder-only models themselves? Could progress in things like encoder-based span prediction, or perhaps constrained sequence generation, eventually eliminate that final dependency on a separate large decoder model altogether, making the entire framework truly self-contained and hyper-efficient?
That's a fascinating engineering challenge, isn't it? How to get that final bit of coherent generation without resorting to the big decoder. Definitely the next frontier.
Something to keep an eye on. Thank you for joining us for the deep dive.
Thank you.
We'll see you next time.